Today we're going to look at some other techniques of integration, specifically undoing the arc sine, arc tangent derivatives. Just those two. We don't worry so much about arc secant. It just doesn't come up very often. So we tend to kind of ignore it. So remember that if u is a differentiable function of x, then the derivative with respect to x of the arc sine of u is 1 over the square root of 1 minus u squared times du dx because of the chain rule, right? U is a function, it's not just a variable. So we could rewrite that as u prime over the square root of 1 minus u squared, as long as what's in the numerator is the derivative of this part that's being squared in the denominator. We can just go straight to arc sine of u. And then for arc tangent of u, kind of the same thing. We end up with the derivative of arc tangent of u is u prime over 1 plus u squared. So reversing those then, the integral of u prime over the square root of 1 minus u squared dx is going to be the arc sine of u plus a constant. And the integral of u prime over 1 plus u squared dx is going to be arc tangent of u plus c. So, and that would be great if that's all that we ever had. The problem is that frequently, I shouldn't say frequently, it'll happen a lot on this, but you sometimes see ones where instead of a 1 being in these places where it's 1 minus u squared and 1 plus u squared, you'll have some other number. And what you do to take care of that is you factor that out so that it becomes a 1. Let me show you what I'm talking about. So let's look at this one, where we've got dx over the square root of 25 minus x squared. So what I'm going to do is for the square root of 25 minus x squared, I'm going to rewrite that as the square root of 25 times 1 minus, and then what would this have to be if I'm factoring a 25 out of x squared?
X squared over 25.
That's exactly right. Yeah, it's got to be x squared over 25. And then what I would additionally do is go ahead and take the square root of 25 and put it out in front. So this would be 5 times the square root of 1 minus, and I'm going to rewrite the x squared over 25 as x over 5 squared. So now my integral becomes the integral of dx over 5 times the square root of 1 minus x over 5 squared. Now going back to this, it says if I have the derivative in the numerator of the u's here, I can go straight to my answer. Well, we actually kind of do. Even though this 5 is here, isn't that the same as putting a 1/5 in the numerator? So we do have that. So once I've done all of that work, this is just the arc sine of x over 5 plus a constant. That makes sense? It doesn't always end up that nicely, but frequently it does. They tend to cook these up so that more often than not they end up nicely. All right, so same sort of thing here. We first have to recognize, okay, that looks sort of like arctangent's derivative, but it has a 9 instead of a 1. All right, let's factor the 9 out. So we're going to have 9 times 1 plus 25x squared over 9. Which is 9 times 1 plus, I want this to be something squared. What would it be? 5/3 x, right? Yeah, 5x over 3 squared. Okay, so I'm going to go ahead and bring the 1/9 out of the integrand. You can leave it in or take it out, it doesn't really matter. This will be 1 over 1 plus 5x over 3 squared. And this one is not quite as nice because the derivative of 5x over 3 is 5/3, and I don't have 5/3, do I? So I'm going to go, okay, let's let u be equal to 5x over 3. Du then would be 5/3 dx. So then dx is going to be 3/5 of du. So now replacing, I've got 1/9 times, I'm going to go ahead and bring the 3/5 out in front also, since it's just a constant multiple of the integral of du over 1 plus u squared. So that's going to be 1/15 of the arctangent of u plus a constant. So that's 1/15 of the arctangent of 5x over 3 plus c. So again, this is one where it looks close to, and this is a lot of why, in my opinion at least, integrals, finding antiderivatives is harder than finding derivatives. Because with derivatives, there's a rule for pretty much everything. For antiderivatives, what you have to do is go, all right, well, it doesn't quite look like I want it to, so I need to manipulate it somehow to make it into something that I can do easily. All right. Then this is another thing that the nice folks at the College Board added, I don't know, several years ago. And I'm like, somebody got a bee in their bonnet about, we need to do more algebra. I'm like, okay, great. In some cases, you can't see that it's an inverse trig problem until you've completed the square. You're like, oh, I haven't done completing the square since Algebra 2. So I'll remind you how to do it. Here, if we just look at it, you're like, okay, I can't do a u substitution because if I let u be equal to x squared plus 10x plus 3, du would be 2x plus 10, and that's just nowhere in sight, right? I don't have anything even remotely like that. And if I wanted to try and solve for x, I've got this quadratic and I'm trying to solve that for x, in terms of u, it's just going to be way, way, way too ugly. So what I'm going to do is go, okay, let's complete the square on this. So here are the steps to completing the square. The first step is one that we don't actually have to do on this one, is if there is a coefficient on the x squared, it must be factored out of everything first. We don't have that problem here. Next, what we're going to do is look at the middle term, we're going to take half of its coefficient and square it. That's 25. What we're going to do is we're going to add that and subtract it. You're like, wait a minute, why would you add and subtract it? Well, what I'm going to do is do x squared plus 10x plus 25 plus 33 minus 25. This is now equivalent to the original. This I can rewrite as x plus 5 quantities squared. What we've actually done here is we've rewritten this so that it is a perfect square. That always happens. That's the whole point of completing this square, is rewriting this so that you get a perfect square. And this is going to be plus what, 8? And now I'm a little closer. I would have the integral of dx over 8 plus x plus 5 quantities squared. All right, well, that looks a little bit more like an arctangent. What do I need to do to make that look more like an arctangent?
Divide by 8.
Yeah, divide an 8 out. And that's where this particular one gets ugly, because it's 8. You're like, oh, crap, that's not a perfect square. I think I had meant this to be a different number so that it was a little bit nicer. Your choice. We can go ahead and do it with the ugly number, or I can adjust the 33 so this is a little bit nicer.
I'll do it ugly.
Let's do it ugly? All right. So I'm going to factor an 8 out, so that's going to be 8 times 1 plus x plus 5 squared over 8. You're like, oh, but I really want that to be, just something squared. Okay, this is going to be 8 times 1 plus x plus 5 over the square root of 8 squared. How's that for ugly? So now I can write my integral that way. It would be the integral of dx over 8 times 1 plus the quantity x plus 5 over the square root of 8 squared. If I let u be equal to x plus 5 over the square root of 8, du is 1 over the square root of 8 times dx. So I'll multiply both sides by the square root of 8. I get the square root of 8 du is equal to dx. So I'm going to pull this 8 in the denominator out in front, so that's 1/8, times, I'm replacing the dx with the square root of 8 du, and I'm going to put that square root of 8 in front of the integral. And this will be du over 1 plus u squared. The square root of 8 over 8, you can leave it that way, or you can make it 1 over the square root of 8. It's the same thing. Depends on whether you like your denominators rationalized or, radicalized. Either way. So this would be that times the arctangent of, and let's go ahead and not mess around. We know what u is. U is x plus 5 over the square root of 8, so let's just go ahead and take the antiderivative and change it back into terms of x at the same time. I think I had meant for that to be a 34, so it came out to be a 9 when you subtracted, and it was, nicer. But All right, let's take a look at this one. You're like, well, with that square root on bottom, if it's going to be anything, it's going to have to be an arc sine. But man, it sure doesn't look like an arc sine at all at this point. All right, well, let's see if we can make it look more like the arc sine. I'm not going to bother writing the square root. I'm just going to deal with this polynomial. And first, I'm going to rewrite it so that it's in descending order. And then I'm going to factor a -1 out. You must factor any leading coefficients out. Now, I'm going to stop right there. Sorry, that should be -1 or -6 here. I'm going to go ahead and complete the square while I'm doing this. So half of -6 is -3, squared is 9. So I add 9, and then I've got a +7, and I'm going to subtract 9. So this is going to be -1 times x minus 3 squared, and that's a -2 times the -1 is +2. So this is 2 minus x minus 3 quantity squared. And now it's starting to look a lot more like an arc sine problem. I know I don't want the 2 to be there, so I'll factor the 2 out. So that's going to be 2 times 1 minus, and again, the ugliness here, that's going to be x minus 3 over the square root of 2 quantity squared. This one actually turns out nicer than you might expect, because all of this is under the square root, right? So when I pull this constant out, it's going to be 1 over the square root of 2 times the integral of dx over 1 minus x minus 3 over the square root of 2 squared. The nice thing about that is when I do my u substitution, u is equal to x minus 3 over the square root of 2. du is 1 over the square root of 2 dx. And that's really nice because that is what I have. I have 1 over the square root of 2 dx. All right, sorry, I left off the square root sign here. So the 1 over the square root of 2 dx all becomes just du. And this is the square root of 1 minus u squared. So that's going to be the arc sine of u, which is x minus 3 over the square root of 2 plus c. And just to show you that it doesn't necessarily have to be polynomials that work this way, I give you this particular problem, and you're like, oh gosh, I really want it to be 1 plus on bottom, 1 plus something squared. Well, it is 1 plus, got the 49. So let's factor out the 49 and see what we've got. So this would be 1/49th of the integral of secant squared of x over 1 plus, well, if I factor a 49 out of that, I'm going to have 10 squared x over 49, which is tangent of x over 7 quantity squared. And again, at first you might think that's just horrible, but it's not so bad because what's the derivative of tangent of x,
Secant squared x.
which is right here? So I'm going to let u be equal to tangent of x over 7. Then du will be 1/7 of secant squared x dx. So 7 du is equal to secant squared of x dx. So now we have the integral. We're going to have 1/49 times the secant squared of x dx is getting replaced with a 7 du, so times 7 du over 1 plus u squared. So that's 1/7 of the arctangent of u, which is tangent of x over 7, all plus c. And there's probably a way to do something with the arctangent and the tangent, but you can't just go, oh, that's x over 7. That doesn't work. Because the 1/7 is part of what you're taking the arctangent of. I don't think you can simplify it. If you can, I don't know what it is. All right, any other questions? So again, let's get in and work it until it looks like something that I can go, oh, I can take the antiderivative of that easily. All right.